I was asked about telling my own story, how I became a physicist. So what I will do is I'll just tell you a little bit about my research so that you have the good feeling for what I do. And then I'll tell you about a little bit of my life story, and then trying to be more informal and relaxed and not too serious. So let's see if I can make it work. As you heard just now, I'm an experimental particle physicist. And let me say a little bit about what kind of research areas within physics that tells you and what my research area belongs to. So I put this chart showing all the research areas in physics. Of course, the STEM field is much broader, but I'm just focusing on physics here. And the subjects that we are dealing with, some research areas are looking at very, very small elements or objects. Some physicists study more human scale. Some study big things like galaxies and stars. So I put this chart for many orders of magnitude. Let me start with the big one, the galaxies and stars. So these are the biggest objects, and we call astrophysics or cosmology. For this type of research, we need telescopes. I'm sure that you are very familiar with the instruments or tools. Then if you go down and you have the more human scale, and if you go even smaller, there are cells, bacteria, and all that. For that, we need the optical microscopes. I'm sure that you have some experience with looking at microscopes as well. But if you want to go and look at even smaller things like viruses or DNAs and etc., then you will need a bit more powerful microscope. We call electron microscope. And now looking at the studying, so those ones we call condensed matter physics or biophysics. Then if you look at even smaller scale, it's an atom size. So that atom size at 1/1,000,000th of a meter, that is about 10,000 times probably smaller than the human hair. That's to give you some sense. So we cannot really see with our bare eyes, but we need the tools to do this kind of atomic physics. Even smaller one is so-called nuclear physics. That is about 10,000 times smaller than atom size. So that's how small that is, and we need the special tools that's called the particle accelerators. And these are, you can think this as ultimate microscope. It's very, very powerful and high resolution telescopes, the microscopes. What I do is so-called the particle physics, and we are dealing with even about 10,000 times smaller than nuclear physics. So that's at all scale, and I'm sitting here. One thing we have discovered the last couple of decades is that just studying very, very small things that make all of us, we call them building blocks, they are very intimately related to the universe, especially the beginning of the universe. So universe history is, age is about 14 billion years. So it started with a very, very small, it's almost like a geometric point, with a very, very high energy and high temperature. It has been expanding over 14 billions, and the universe became very cool now. So anything that we are studying in particle physics, very intimately connected to the beginning of the universe. So you'll see quite exciting how things are connected to each other. In fact, we need to know all of them to understand how the universe works. It's not just one area. So now, talking about particle physics, and just tell you a little bit more about that. So I'm sure many of you have played Lego blocks, making object houses and boats and trains. So I'm sure that you're familiar with it. By the way, I never played the Legos in my life when I was young, because I grew up in the countryside, and all we had is dirt and stones. I never had the Legos. So I see the kids are playing with the Legos, and I have to go and try it even now because it looks so fun. So we make this nice object and big object in the Lego world. And then you may ask, what is the Lego world made of? Another way of asking is, what are the smallest thing? What are the building blocks of Lego world? So you may have already guessed by now the Lego blocks. So there are only a few kinds. You see there are the shape, there's only the blue one, there's a small one, and there's some bigger ones and red one. So there are only a few kinds, different kinds of Lego blocks. Each kind, there are many of them. So depending on how many you put together and how you put together, you can make a house and the bridge and things like that. So these are the concepts, and you can apply the same concept to the real world. So this is a beautiful Korean dance. So there are you and me and any object we see. So what are we made of? What about the earth, anything object in the earth and even space? So the question in the world might be, what is the world, real world made of? Another way of saying is that, what are the building blocks of the world? Or we can say same thing as, what are the smallest thing that makes all of us? Something very small and fundamental, elementary, and depending on how you put together, assemble together, we can make very different objects. So the question is that. And this is exactly the question of a particle physicist like me. So that's one thing, but there's some more. So for Lego world, of course, human beings are like a glue because we assemble. But in real world, there are building blocks. But then how they are assembled together make you and me and all the objects in the universe. So in the real world, that role is played by the forces. I'm sure you are very familiar with the gravitational force. That's how the Earth can be orbited around the sun and the solar system and galaxy and all that. Make all the stars and galaxies is really due to a gravitational force. And there are other forces called the electromagnetic force and weak force and strong force. So there are 4 forces in nature to make all of us. So that's, we are also studying that more in deep level. So connecting building blocks, first we have to find them, and then we have to watch how they interact, what kind of forces between them. So that way we can understand how the world works. So now thinking about building blocks, so let me go back about in 2,500 years back. So this Democritus from Greece, so he thought he's not experimental, so he cannot really test anything, but very philosophically, and also he's seen a lot of things and behaviors, and he had a notion that the world, there must be building blocks. Let me call atom. Atom, the meaning of atom is indivisible. So that means that you can chop yourself or any object, pieces, until you cannot chop further. So that means that's the smallest things you can think of. That's what he calls atom. So with that, then he thought that universe is composed of atoms and the void where atoms move around. And that was his, suggestion and how the world is composed of. So then in addition, he thought that it's not, there's one kind of atom. That's what we saw the Lego blocks. We sometimes have a few kinds, different styles. And he thought that there are numbers of different kind of atoms. The masses will be different, but they look like a more this sphere look, but size and mass would be different. But these are very, very small, so you cannot see with the bare eyes. So very, very conceptually thought through. So then the atoms then thought to be building blocks of the world. So now we are curious whether his theory is really true or not. So we have to test it out. The question will be, are atoms really building blocks of the real world? Another way of saying is, are they really the smallest things in the world? Or the question will be, that may not be the case, maybe made of something even smaller. So that's what we want to test it out in the last century or so. So let me see what we mean by seeing. And when we say, okay, we observed and we discovered something, or we've seen something, and sometimes what we mean is from our eyes, but sometimes with other tools, because our eyes have very limited the visibility. But let me start with the things we can see. We can see the sun because the sun radiates light. So to our mind, the light is also a particle, kind of particle. And we see the sun because they emit light and is a particle or particle beam. And then I see you, and you see me. That's because the light, in this case, not just the sun, but this light over there from bulb that emits light ray and light beam, and then hit you, and then come to my eyes. So again, light goes here and reflects that light, and then come to our eyes or cameras, so we capture that. So this is a sort of the detecting device, and this is a sort of particle source. And so particle beams going here, and then we see how that scatters, and then from that information, and we get to see you and me and each other. But what about something very small, like bacteria and all that? That's we cannot see with our eyes. We need the tools. As I mentioned earlier, microscopes are such a tool. In this case, we use electrons. This is another particles. They use electron beam. So this machine creates electrons and the accelerate. So electrons have high energy. And they hit the, in this case, the breast cancer cell, and coming out from that reflection from this way, and we have another detector device here, and see how that responses between here and there. From that information, we can see, this is how the breast cancer cell looks like. So that's how it goes. But what about things even smaller one? We are talking about atoms. Atoms are much smaller than those bacteria. We have the same concept. We need electrons or protons, this kind of particles. But in this case, if you want to see something very small, we need a much higher, more energy pumped into these kind of particles, so that with that, and then check it out how they react with the atom, and from we put the detectors somewhere there, and then see how this reflected beam, the information is like. And from that, we can put together and say, this is made of, maybe this is a solid sphere looking, or maybe different looking. So we have to check it out whether atoms are building blocks in this way. But in our case, we want to see something even smaller. If an atom is made of something smaller, we need not just a high energy particle, but we need a very high energy particle. So now if we want to see something smaller inside of atom, and we need a very high energy particle beam, and then just to see that how they react here, respond, and we detect that information in our detector device, and then see whether they are made of something smaller, or maybe atom is indeed the building blocks. So that's how we do. What have I done? Oh, okay. So now, so how do we make this very high energy beam? That's what we use, so-called the particle accelerators. So you start with electrons or protons, these kind of particles, and we pump a lot of energy into these particles and make a very high energy beam. So you see, this was created by the Ernest Lawrence. He was a professor at the University of California, Berkeley. And so 1930, he invented this accelerator. So again, accelerators are nothing but you put the battery, very strong batteries, and with the help of the batteries, the particles, charged particles, can gain more energy. So that's, and becomes a higher speed. That's what happens. But that is almost 90 years ago. And during 90 years, there have been many generations of accelerator, the improved and has a much better and better performance, because we had also had a better technology and better science that helped making really, really gigantic and outstanding accelerators. So the current, the most powerful accelerators in the world, and these are very, very big. We are talking about 10 kilometers and 20 kilometers underground, the tools and equipment. So this is not something that one country can build. These are rather expensive and require many expertise from various kind of scientists and engineers and technicians. So usually done by international collaboration. So one is located in Geneva, Switzerland. So this ring actual accelerator underground, as I said, about 100 meters below the surface, covers some part of the Switzerland, some part of France, but the location where scientists work together, that's located in Geneva, Switzerland. So that's the big accelerator. A different kind of accelerator, and also needed, So that's where the Fermilab is the Chicago area has also the accelerator. You will see this one ring is about 6 kilometer circumference, and there are 9 accelerators put together and make a very great performance there. And then there's also a very powerful one in Japan, and the Tsukuba, a city called the Tsukuba. It's about 1.5 hours by car. So that's also there, have a wonderful accelerator there as well. So these are gigantic accelerators. Again, they are not only pumping a lot of energy, but also many particles are needed to do better research. So it's rather the important, accelerator itself is now new scientific research area. And then as an experimental particle physicist, we use their beam and have them this colliding to another material or beam-to-beam collisions and see what happens. And we build the detectors around the collision area and see what has happened during the collision. So with all that, I started with the atom, with the higher and higher and better accelerators in the last the 80, 90 years. We know that first we discovered, the scientists discovered much before me, that atoms are not the building blocks, but they are made of electrons and nuclei. I made the nuclei very big, but the nuclei themselves are 10,000 times smaller than this atom size. So when this was, the big discovery was made, again, the public was very surprised, and scientists even more surprised. And also the fact that nuclei, the fact it's very, very small is surprising. But also all the mass of the atom goes into very small nuclei. So nucleus, by the way, means a small nut. You know, you have a fruit and nut, it's a small things, and it's kind of dense, that's what it is. The scale of the comparison of atom size to nucleus size is such that if you think of a big cathedral you often see in Europe, huge, gigantic cathedral, if we say that is the size of an atom, and imagine a fly in the cathedral. That's how small the nucleus is with respect to atom. Not only that, that's fascinating. Not only that, imagine entire cathedral weight goes to the fly. So that's about how you can imagine. But also, it does not really shown here, but if you look at inside of atom, almost all area, more than 99%, is just empty, void. So there's in the core nucleus located, and electrons, which is a very, very tiny and light, much, much lighter than nucleus. They are just orbiting around. So this is a very void, empty space. And that's very similar to, look at our solar system. Of course, look like we are very dense areas. But if you step out and then look at the solar system, pretty much all empty. In the core, we have the sun. And then we have a planet like Earth going around. But these are very small amount of volume compared to the big solar system. So to me, thinking about the atom and how it looks like inside is like similar to what the solar system. And so inner space and outer space, and that's kind of nice similarity. But then it took several decades to find out that nuclei, they are not the smallest. They are made of another particles called the neutrons and protons. With the even better accelerators and bigger and more complex accelerators, we learned that they are not building blocks, and they are even made of even smaller things called the quarks. So now, as of now, we know that the building blocks are up quarks and down quarks and electrons. So it doesn't matter what kind of atom element. It's carbon or oxygen or uranium, any the atom you go, if you look at inside, they are nothing but made of electrons at up quark and down quark. So the number of quarks and number of electrons are different for different elements, but everything is made of that, and that's very fascinating. So these are big accelerators. I told you this is gigantic and done by collaborative work internationally. So there are 3, Fermilab in Chicago area, and CERN in Geneva area, and Tsukuba area, KK. So my life has been, here's the South Korea. So my life has been going to different locations. So in fact, all the particle physicists around the world, their home institutions are in all different cities and different locations, but we travel to these accelerators and to do our research. So that's how you'll connect to why I just hopping around at different places later. So I followed at a given time, what's the best accelerators for my own research. So when I was doing my PhD in US, I used accelerator in Japan. Just gives you a scale that's about 3 kilometers. And then all structure here is above surface, but accelerators are below the surface. Then later on, I did my work with this using accelerators at Fermilab. That's each one is about 6 kilometers. So you can imagine that has been big jump and become bigger and better. Now I'm working on the experiment using another accelerator at Geneva at CERN. So my sort of journey has been following higher and higher accelerators. And I said that if you have particle beams colliding to each other or colliding to the matter and detector, you have to build around this the collision area, because I want to see after collision what happens, and we have to detect, like our eyes, we have to build a very, again, complex accelerators. So that's what we do, and then we do data analysis as well. So when I studied the PhD research in Japan, this was the size of collaboration. It's about 60 physicists particle physicists from 4 countries. By the time I came to CDF experiment at Fermilab, it was about 300 particle physicists from dozen countries, and that grew to up to 700 physicists from 20 countries. So I'm here, there, and this is another one working on the detector. And when I am here with the Large Hadron Collider CERN experiment called the ATLAS, you'll see the scale of a human being to the scale of the detector. So that requires many different experts and skill sets, so we need quite many people. I didn't mention this one, but there's a huge development of computing as well. And when we deal with this kind of detector technology, this technology usually doesn't exist. So we have to really develop a new technology and design it and try it out whether that concept works, and then you build it. Of course, if we will build all that, we know the technology, we can give this technology, either detectors or accelerator technology, we give that back to society so that the other companies can use this technology for their products. So that's how research can go to helping the society. So again, my journey is following the better and better detectors. So I mentioned that the universe has been expanding 14 billion years. So this is one cartoon starting from universe called the Big Bang. And you kind of show that there's a jump, big expansion very, very quickly, and then continue to expand. So there are, at the beginning, very high energy particles, the high energy and high temperature. There are a lot of particles that they may not exist in the nature now. But in that kind of very high energy environment, high temperature environment, certain very exotic particles existed, and then I'll say a little bit more later. So now we have, this some point, some billions years later, we start building the stars, and finally we have here. At the beginning, we don't have any atoms or anything like that. All these building blocks particles just like soup and moving around. And by the way, so this is a very famous chart that a lot of physicists and scientists use, and they only show the thinking man. So this was my invention of adding. Whenever I have a chance, I have to add this one. So if you just pick it up, Google or any posters, there is only thinking man, and there's no thinking female. So I searched Google some years ago, and so there are a lot of thinking woman or thinking female. You try it out. There are some cases very unexpected photos that show up on the screen as well. And I thought that this might be the best, at least based on what I've seen, all the different photos and statues. Because this is a very thinking of it, and actually they both are it's naked, so I have to find some picture or statue of a naked female, but it's covered enough so it doesn't look bad. And so I just put that, and it's also really look like Asian too. So I thought that maybe it's just resembling even myself. So I mean that's the society, right? They think thinking or science and technology or engineering, they think of a man, not think of a woman. And so we have to, it's a people like that, that's a culture, and we are brainwashed. Even women often not think of men, think of ourselves, a woman, as a scientist or engineers. That's because we were kind of culture really trained us, brainwashed us. So we have to try to brainwash back so that female figures always come here. So anyway, with thinking human beings, we invented and all the tools and curiosity of understanding the universe. That's what I showed all that. Whether quarks and electrons are the really building blocks or not, that's a remaining question. It might be something even smaller. So in the future, your young people in your generation, with even more powerful accelerators, you can even get to find out that, hey, you are wrong. There's even smaller things, and you'll see, but that takes time. So when we are doing that, I said these are high energy accelerators. That's very similar to what happened very, very early universe. So high energy accelerators, meaning that we can create some conditions of the beginning of the universe. So by doing that, we are also looking backward in time and creating this, what happened there. That's where we can understand the early universe. And that means that we can understand how the universe evolves where we are. With that, we can understand how the universe will evolve in the future. So there's a very tight connection between really inward and looking at small things to the beginning of the universe, and together we can create the elegant or more complete theory. So now let me say a little bit about my childhood to where I am, and how I got here, sort of stuff. Okay, before that, so I'm sure you know very well, but especially those who came far, just want to give you some idea where South Korea here and North Korea, and this is China, and this is Japan. But you may or may not notice before, this is Russia. So there's one of our neighboring countries is Russia there. So when I was in the elementary school, typically this is how we learn, our self-centric. So South Korea and 3 countries around us, Japan, China, and Russia. And then later on, I realized that Russia is much bigger than just around here. Again, this is Korea, North, South, Japan, and China. And Russia, in my view, when I was young, I thought it was just here. But later on, realized it's all the way connecting to Europe. So this is a more European side of Russia, and this is the Asian side of Russia. So that kind of tells you also, it's a lesson for me too. When you think about it, often you think about very narrow view, and that's often wrong. And you have to really step back and just look at the big picture, because just looking at your own view, and often you miss a very important truth. So that's Seoul, and this is where I was born and I grew up. Give you some orientation. Here there's a big, the second biggest cities in South Korea. It's called the Busan, and Incheon is also big somewhere here. Around here is called the Daegu, and one of us big cities in South Korea. I grew up in apple farm, very small countryside. This is my parents. They got married in 1950. My father and my mother, a very traditional wedding. And my family, this is my grandmother. She lived 99 years, so it's very long-lived, my grandmother. And my mother and my father. And this is my big brother, eldest sibling. And then my big sister. So boy, girl, and then we had 4 more girls after that. So we are 6, and I'm number 5 of that. So, and so in year 2000, we all 6 siblings. We do that every year. Whenever I come here, this is all family get together, especially 6 siblings. We get together to spend our own time. This is my mother, and so this is my brother, eldest one. This is my big sister, number 2, number 3, number 4, number 5, and number 6. And now with this family size group, because everybody got married and has babies, we have like 30 people from my parents down. So in 2000, my father passed away, but my mom is still living in this home. So this is where behind is our apple farm. And my mom loved the gardening, so she just planted, my father helped too. So it's, our garden is always beautiful with a lot of flowers. So that always kind of very nice. My parents, they were not rich, being in the countryside and farm. Sounds very exciting, big, but you Koreans know apple farm doesn't mean it's a really small business. So supporting the 6 children education is very, very tough. So they borrowed a lot of money actually to educate us. But they believed in the education, so support any educations we like to pursue. And one remarkable thing is that they don't expect that since we a lot of pain to get you educated, and now it's a time for you to pay back. They never said that, so they think that's a good thing. Another amazing thing is about my mom. She got only elementary school education, so she never even went to high school or junior high school. But my father went up to a high school. So these 5 daughters, and she does a lot of farm work. My father's, it's very weak and sick most of the time, so most of real work labor work is done by my mom. So then we say, okay, we want to help you or farming or cooking and cleaning. My mom would say, you can help a little bit, but not much. I don't want you to be good at farming or cleaning or cooking. Because if you are good at it, you become farmers, you become cook. Nothing wrong with a cook, but her mind is that you have to go away. So that's her philosophy. I don't know where she got that from, but she's right. Many ways. So she always pushed away. It's good that you help us a little bit because that's a family has to help each other and you have to do it, but don't be good at it and get out and get educated. So being number 5, actually there's a lot of the opportunities. That's because usually parents are number 1, number 2, they pay more attention to make sure they don't get hurt and all that. But after number 5, do whatever you want. They don't see me. They don't see me. Number 6 is bad because my younger sister, she's the youngest one. So parents, kind of feel sorry for the young one because, this is a little one and they don't get to see parents as much as the other siblings. So number 5 is a very good position. So I do a lot of crazy things and I don't lie, but I never tell them what I do. Unless they ask, and they don't ask, so it's very good. So I looked at my photos. Interesting enough, again, growing up in countryside, that they don't take photos except my brother's first birthday photo exists. But the earliest one is when I was in elementary school. So this is one of the earliest the photos I could find. This is a sister above me. So I did my education up to junior high school in hometown. Then high school, that Daegu is one of the big cities I mentioned earlier. So it's a girls' high school. Many high schools in Korea, we separate the boys and girls. I see many good advantage too, because you don't pay, when you are teenage girls and boys, you know what that means, right? So it's trying to be really look cool and look nice and all that. There are other distractions. So for me, high school time, just girls ourselves was a really good, many ways, education as well as some other bonding and the fun. Oops. Okay, so when I was the high school, by the way, so this is some of you may know, this is a typical high school uniform. So this is a school to school, that's a little bit different, and this is the uniform that my school had. So what I'm going to tell you that what I did, I tried a lot of different things, and if I think about what I love the most and spend the most of time, is doing a lot of things, the dancing and singing and all sorts of things. But I also love the math. So there are 3 things I did mostly: dancing, singing, and doing math, because I enjoyed much. Singing is something that I really enjoyed it, but it was an interesting story. That once I was walking the street and heard the beautiful harmony coming from the church. So I went in. I'm not religious. My parents are not Christians or like that. But just I went in and I asked the conductor whether I can join the choir even if I don't come to church. for religious reason. And he said, sure. So I ended up joining choir, and I had a lot of fun doing that. So of course, then church and schools sent me to various competitions. So that was kind of fun. So these are some of photos that my dancing time and then singing and stuff. Now, I went to the middle school. I said I enjoyed the math just because I don't know why, but so I did my own the solving problems, and that was fun. But I didn't have much of a science education at all until I went to junior high school in the village, the countryside. And at that time, at least our province, it's for you, Gyeongsang-Bukdo area, there's a science competition. It's more kind of school to school. In the small region, whoever the winner became bigger competition. So it's a kind of tournament, a region to region tournament. So one of our science teachers asked me to join that, our school team, and I said, well, I don't know much about it. And he said, well, I'll teach you. So I don't know still why he chose me, but I was chosen very gratefully. And so once a week was a couple of hours, we learned the physics and chemistry and biology and geology and all that. And so so I got more education, and I was, somehow enjoyed it. If you enjoy, you do better, right? So I ended up really winning the entire Gyeongsang-Bukdo competition. And that's another story, interesting story. So every year we had this tournament. So the radio station announced the winner. So they said that my name, Young-kee Kim, is a winner of this year, and they called he. They thought I'm a boy. Obviously, I'm a boy to their mind. By the way, my name is also a boy's name. Sounds like that's why. So I cannot criticize too much because and also in the past always the boys were winners, so they were surprised a bit. They corrected that at the end. So, but having that experience, by the way, so I also had a very nice the interactions and became friends with the girls from other schools who joined the science team. So I'm really fond of especially these two girls that I worked with. So certainly being trained there and etc. Gave me some confidence about my science skills. So that certainly helped quite a bit. Then went to high school in Daegu. I told you, and in Korean system, high school system, the second year, you divide sort of more science and math type. Eventually you want to go, or you are more literature, arts, and laws. And so we have to divide it. So education is slightly different. Science type or engineering type, you get more the math and science education, and the others the other one. So I have to make the decision on whether I choose this or not, because I love the singing and dancing. So this is a possibility, and I thought, I'm short, I cannot be real good ballet dancer, so I know myself, so that's not my career. But certainly I enjoy the math and etc. So that's my choice, and that was not difficult for me, I must say. So then I went to the Seoul Korea University for my college education there. So that's a photo around that time. So there, when I entered the university, I thought I'll major math. That was my thinking. Then, after 1 year, I have to make a decision. That's really the major I want to choose or something else. But during the first year in the college, I had a more opportunity to read and study, other parts of the science, and really started enjoying physics. So after 1 year, I have to make decision. I didn't really know whether I'm really good at physics or I really enjoy physics, but kind of going that direction. And math, I knew for sure. So my thinking was, well, I'll try physics, and if I don't like it, I don't think I'm good at it, or I don't think I like it, then maybe I can change to math. So that was my thinking, and chose physics. I guess I really loved it. So that's my choice. But then instead of experimental physics, I thought I'll be a theoretical physics is my thing, because I love math, and it's obvious choice. That's my thought. By the way, in terms of the choosing, again, reading books and studying and all helped me, but one of my professors in the school, the Chu Sang-keng, he really influenced me in choosing physics. When he gave lectures and physics lectures, so crisp, clear, and so much fun, and I just feel like everything comes to my brain and becomes mine. So he influenced quite a bit. So teachers' roles in general, I know, as you know, it's very important. Even junior high school, when I in science competition, the science teacher picked me and helped me just understanding all the science education and training. So that's roles of teachers are pretty good. But my love of dancing continued. I was very good at joined the max dance, the club, and so that continued my dance love. Then I came to University of Rochester, East Coast, for my PhD, and there also I met the professor Steve Olson, who is an experimental particle physicist. And then he just gave me some projects the first year at the university, and it's an experimental one, and I loved it. So he also helped me changing from theoretical to experimental. So again, he's a very good mentor for me. So as I said, that I did work, the experiment was located in Japan. So I was a student there, but after 1 year of a class, and I moved to this laboratory and did 3 years of the PhD studies there. So of course, it's also a lot of fun with the friends. It's very important for me. So after that, I did a postdoc and then became professor at the University of California, Berkeley. So that's, I moved to West Coast, but my experiments again followed oops, I'm going too much. My experiment was located at the Fermilab. So while I was a Rochester student, I did experiment there. After that, when I was at Berkeley, I did experiment at Fermilab. So this door-to-door, it takes about 8 hours. So 4 hours flight by airplane, and then going to the airport and airport to Fermilab, so 8 hours. It was a tough, and teaching and all that, it's tough, but I enjoyed it very much. So during that time, I would say I have a very good mentors. The one is the Melissa Franklin. She's the professor at Harvard, and we did the working together in some of experimental work at Fermilab, and she influenced me and helped me quite a bit, guiding me. And another person, the Pierre O'Donnell, he was then deputy director of the Lawrence Berkeley Laboratory there, and he was also or somebody I always easy to talk to and give a lot of guidance from him. So there are, again, having good mentors and teachers are very important at any moment in your career. In 2002, I got married. This is another Korean traditional wedding in Daegu. And it's more colorful, color photo. And not like my parents, we can be a bit more playful at the wedding. So after 2002 wedding, we are teaching in different universities, so we have to, so-called the two-body problem we have to solve. So we have, lucky that we have multiple opportunities to go different universities together, but we chose the University of Chicago, and so 2003, we became both professor in physics department there. And then at that time, I continued to work at the experiment at Fermilab. And later on, I became the leader of the entire experiment. It's actually 600 or 700 physicists. And everybody, including students, they voted. So they elected me as their team leader, entire group, which was very, to me, it's touching. This probably, there are a number of experiments in physics. If you count any group, more than 100 the people in the team, so we are much bigger. I must say I am the first one who were elected as a team leader that I know of. So it was a little bit of a transition, important moment, critical moment for me and for our community as well. And people are coming from all over the world. You can kind of sense from how they look, and they are really coming from all over the world in 20 countries. So after that, I was asked to be a deputy director of a Fermilab for 7 years. So just give you some idea what typical laboratory that's a Fermilab or CERN or KK lab. So it requires many people from physicists to engineers and technicians and computer scientists and administrators. And this is like a small town. So Fairham's case of 2,000 employees to helping building and the accelerator complex and also running, operating. And then like about 2,300 these scientists, particularly experimentalists from all over the world come here to use that equipment. Like me, I used to come from here to there, from here to there. So that like us, using that facility, we call users. So you'll see we are dealing with the 4,000 people, such a small town. From lab, even we had the fire department, it just gives you some idea. Not only that, we have daycare centers at the lab from infant to 6 or 7 years old. So as a deputy director, and he is the director at that time. So we have to, pay attention to not only scientists and technicians and engineers, but everybody, including these little kids. Then we also had the bisons, American bisons, or buffaloes. So when Fairham's was first established in 1970 also, that they invited or adopted this about 100 bisons, because they symbolize a frontier. Even in the western side of the U.S., they are tough in snow or cold weather. They're really tough and sort of representing the frontier. So Fairham's Lab is a frontier of science, so it's nice symbolism. So we have the people also taking care of these buffaloes. So you can imagine, director and deputy director, we have a lot of things to do beyond the science. But that's when I also learned that when you do science, in the science team, I was the leader of the big science team, and we care about science, but we often forget about what else is going on. And running the complex, accelerator complex like that, it's not just scientists. I said that there are hundreds of, about 300 of engineers and 400 technicians and computer scientists and administrative people, even people who are taking care of the kids so that their parents can do good research and taking care of that, because it's having animals and this kind of thing also helps us thinking or a different atmosphere, very friendly atmosphere. It's important to do better science. So that one, I realized how much of hidden heroes to make science better. So that's a lesson I learned. Then I said I'm working at CERN right now. And in addition to particle physics, I realized that we heavily rely on accelerators, and we have not really educating enough accelerator physicists in the world. So I myself is now started doing accelerator physics and training accelerator physics students. Just a couple of last slides. I continue to enjoy, even now, the dancing. To me, I travel a lot, the nature of my research, travel a lot. And if I go someplace, have a little bit time, and a week or 2 weeks I stay, I already trying to find a teacher of traditional dance at that location. Because for me, when you travel, you want to learn, you go to museums, you go to cathedrals, and also traditional places that are famous for that area. Why do we do that? We want to learn culture and history. For me, the dance also captures all that. Physically, by learning that, you have a good connection to that regions and culture and history. So I love that. So I continue that. And I mean, I'm really also crazy about gardening. So we have a big area for gardening. I continue to work with that. It's very feeling good, right? This is a therapeutic sometimes, often, and keeps you relaxed. But most importantly for me, it's the flowers and plants that they are very honest. If you put effort, of course that's not enough. Nature sometimes helps too, but they respond a very honest way. So it always kind of remind me of anything we do has to be done in an honest way. So in my father, the late father, who is very good at calligraphy, so this is his writing. And he gave this to me some years ago before he passed away, and this is very important for me. Also, very meaning of this calligraphy is it's something special. So I'll explain that to you. So the first one is called the kyung, that's respect, and chun, that's heaven, but to scientists, this is the universe. So respect the universe. To my mind, respect the laws of nature. So that's what we do. All the science we study, we want to understand how the nature works. What's the laws of nature? That's what we are doing. So I respect the laws of nature, so that's what we do in science. And the third one is love, in people. So love people. And science is done by people. So especially at the research I do, I showed you big collaboration and hundreds of people, and now it's even 1,000 people working together. We have to really respect who they are, respect that people are coming from all diverse the training and culture. And they're different. We have to respect their culture and really loving and respecting that's the way science has to be done as a collectively, all the brilliant new ideas coming because of all different culture clashes, then something exciting comes out. Just all the same or the same kind of people, their thinking is very narrow. You don't get something out of the box. We need something breakthrough that often comes from diversity, people and diverse background skills. I believe in that. So with that, thank you for your attention.